Okay, so far what we've done is we've taken a look at pressure, volume, temperature, and moles using the gas laws that we've talked about. Boyle's law, Charles' law, and Avogadro's law. All of those conditions were under changing conditions. In other words, we took the pressure and we changed it and observed what happened to volume or temperature or moles. Or maybe we changed two of them, pressure and moles, and then saw what happened to volume. So again, all of those conditions were changing. Well, what we're going to look at now is what we refer to as the ideal gas law. And we're still looking at pressure, volume, moles, and temperature, but now we're looking at what we refer to as a steady state. In other words, our conditions aren't changing. We're looking at what would the pressure be if volume were this? What would temperature be if the moles were this? So again, up here with the combined, we were talking about changing states. Here we're talking about a steady state. Okay, the same way that we came up with relationships with volume and moles, volume and temperature, volume and pressure using those constants B, A, and K. If you remember back when we started with Boyle's law, we talked about our three experiments, and then if we said if we took pressure times volume, that would give us the constant K, and we did that for the three variables, volume, temperature, and moles. If you combined all of those, what you would get is what we refer to as the ideal gas law. Pressure, volume, moles, temperature, and then we have this other variable which we call the universal gas constant. Now there's lots of values for the universal gas constant depending on the units you use, but what we tend to use are units of liters, atmospheres, and kelvins. Liters and atmospheres are going to dictate this value. In other words, if we were to use, say, milliliters and kilopascals, that number would be different. It would make our calculations the same, but the value there would be different. So if we always use atmospheres for pressure, liters for volume, our gas constant will be that value, 0.0821. And usually we usually write 0.0821 liter atmospheres per mole K. So again, we use this equation when we have a steady state. We use this equation when we have a changing state. So let's do a couple of problems. Now we'll have much more in-depth conversations about the gases. However, in this vodcast, all we're going to do is look at how we solve problems using the ideal gas law. So we've got an automobile tire with a temperature equal to 23 degrees Celsius. When it has a volume of 25 liters and it's filled up to a pressure of 3.18 atmospheres. And then it says determine the number of moles in that situation. Now notice we're not changing anything. It doesn't say change the temperature from this to this or volume from this to that. We're saying at this temperature, volume, and pressure, what would be the number of moles? So when we have a condition where we're at steady state, we're going to use the ideal gas law. Now let's go through and do a couple things. Let's make sure our temperatures are in kelvins. So we can change that to 296 Kelvin. Our volume is in liters and our pressure is in atmospheres. If our pressure here wasn't in atmospheres, we would want to convert it to atmospheres. So let's plug in our values. Pressure, 3.18 atmospheres. Our volume is 25 liters. We're solving for moles. Our gas constant is 0.0821, and I'm not going to write the units to save some space. And then our temperature is 296 Kelvin. So then when we solve for moles, we get 3.27 moles. So again, make sure your units are consistent with the gas constant. Liters, atmospheres, moles K. Make sure your temperatures are in kelvins, and then just make sure you're doing the math right. Okay, let's take a look at another problem. What is the pressure? And again, notice when I'm reading these problems, I'm writing the variables down as I'm reading it. It just helps organize the problem as you go to solve those. We have a 304 liter tank. It contains 5.67 kilograms of helium at 25 degrees Celsius. Now notice I didn't write a variable for this because it's kilograms. It's not pressure, volume, temperature, or moles. So we have a steady state, so we know we're going to use PV is equal to nRT. But now we have kilograms of helium. Well, hopefully you already see where this is going to go. If we have kilograms, we can convert to grams. So we can say 1 kilogram of helium is 1,000 grams of helium. So our kilograms cancel. And then you know you can convert from grams to moles using the molar mass from the periodic table. 4 grams of helium per mole of helium. So our grams cancel. Let's do the math. And we get 1,417.5 moles of helium. Now that might sound like a whole lot, but look at our values here. 5 kilograms of helium, that's a lot of helium. And that's in a container that's pretty large, 304 liters. So when we plug our values in, pressure, 304 liters, 1,417.5 moles. 0.0821 is our gas constant. At a temperature, now we need to convert that. That'll convert to 298 K. So we can put that in. And then we can solve for our pressure. And we get 114 atmospheres. Now that's a pretty high pressure, but again, we have some pretty extreme conditions here, so that should make sense. And you might want to go through and double check the math, but that should be fine. Okay, let's take a look at one more problem. We want to find the temperature. At what temperature in Celsius does 121 milliliters, so our volume, 121 milliliters of carbon dioxide at 27 degrees Celsius and 1.05 atmospheres can occupy a volume of 293 milliliters at 1.4 atmospheres. All right, so we've got a lot of variables here. So we've got different temperatures and different pressures. So let's try to separate this a little bit. We have, let's just say condition 1 and condition 2. So we have a volume 121 milliliters of carbon dioxide at 27 degrees Celsius. So 27 degrees Celsius and 1.05 atmospheres can occupy a volume. So now we have a different volume, 293 milliliters. We have a different pressure, 1.4. Whoops, sorry. Let me rewrite that. 1.4 atmospheres, and we're trying to find the other temperature. So what we have here is a condition where we're changing conditions. So what we have is a situation where conditions are changing. So we can set it up. 1.05 atmospheres, pressure, times volume, 121 milliliters, over our temperature of 300 Kelvin. Set that equal to our new pressure, 1.4 atmospheres, 293 milliliters, and then solve for the new temperature. And we get 968 kelvins. So the point of this problem is realizing that you have to differentiate between changing conditions and standard conditions. Or not standard conditions, but steady conditions. Okay, so we've looked at all the gas laws, and we've looked at we've combined 3 of them into PV over T times N is equal to PV over T times N. That's for changing conditions. And now we have PV is equal to nRT when we have steady conditions. And again, what it comes down to the gas laws, at this level anyway, until we start really investigating them, is practicing these problems. So practice the problems in your work packets, and as usual, email your questions to hannonandchemistry@gmail.com.